Hello, this is Dave Soraka, Madison College, Calculus 3, spring of 2017, and this is the video lecture that I have asked my students to view, and that is taking the place of our regularly scheduled class meeting for Friday, March the 31st, when I will be out of the office having surgery on my foot. And I would simply remind you that I'd like you to view this video in its entirety by the time we reconvene next Monday morning. So what I'm planning to do here, and I'm only going to plan to go about 50 minutes, so if I'm not able to finish all of the examples by about the 50-minute point, I'll quit and we'll finish things up on Monday. On Thursday, we began talking about triple integrals. And so what I would like to do here is look at some specific examples to illustrate how to go about setting up appropriate limits of integration for a triple integral after determining an appropriate order of integration. So here's what we're going to talk about. Now let me quickly recap what we talked about on Thursday. A triple integral is one in which we have some function of three variables, and let's for now presume that we are in the rectangular coordinate system. Later on in the chapter we're going to talk about some alternative coordinate systems. So just like we have the polar coordinate system as an alternative to rectangular coordinates in 2 dimensions, there are a couple of alternate 3-dimensional coordinate systems that we may consider using if the rectangular coordinate system turns out to be problematic in 3 dimensions. But for now, rectangular coordinates it is. So let's say we have some function of 3 variables x, y, and z, and some solid d, like the one that you see in this first example here. So we need to determine an appropriate order of integration as part of the process of evaluating this triple integral. We talked last time about how to take care of things computationally once the integral is set up, and it's very much a natural extension of what we do for double integrals. So if, for example, we were to integrate with respect to z first, then x, then y, so let's just suppose, for the sake of argument, that this dv is replaced with dz, dx, or say dz, dy, dx. When we evaluate that innermost integral with respect to z, we treat x and y as constants. So we perform a partial anti-differentiation step with respect to z, treating x and y as constants. And then we plug in our limits of integration in place of z into that antiderivative. That makes z permanently disappear from the problem. And from that point on, the problem looks just like a double integral with respect to y and then with respect to x. And we know what to do there. We're integrating with respect to y next. We would treat x as a constant and anti-differentiate with respect to y, plug in the limits in y, and then at that point we have just a function of x that we integrate with respect to x, and then we plug in the constant outer limits. We also motivated why we would want to perhaps consider this thing that we call a triple integral. For example, if we wanted to compute the mass of the 3-dimensional solid d, this would be a density function. So if the solid has variable density, what we would need to do, at least in theory, is break up that solid into little tiny pieces, because as long as those pieces are small enough, then the density can be considered approximately constant inside of one of those little pieces. And if density is constant, then the mass is equal to the density times the volume. And so you take your constant density approximation for that tiny little piece, and you multiply that by the volume of the piece. And if that piece is just a rectangular box, then its volume is just its length times its width times its height, which would correspond to delta x times delta y times delta z. And then we add up all of the mass contributions from every single one of those little pieces, and that gives us a Riemann sum that evolves into a triple integral as we let those pieces become infinitesimally small. Okay, so those are the basics that we talked about on Thursday, but what we didn't have time to talk about is how to actually go about determining an appropriate order of integration and appropriate limits of integration for a given three-dimensional solid. So what I first want to do before we jump into this first example is remind you of the thought process that we go through when it's a double integral over a two-dimensional region that we're trying to set up. So if I have to compute the double integral of a certain function of two variables over some region R, and I need to determine whether to integrate with respect to x first and then y, or y first and then x, that decision will likely be made based on what that region actually looks like. If it happens to be a region that looks something like this, so say we've got a curved upper boundary and a curved lower boundary, but lateral boundaries that look like vertical line segments, then I would probably integrate with respect to y first and then x. Because if we choose an arbitrary point inside of this region, and we want that zero-dimensional point to evolve into a one-dimensional line segment, I would rather have that point evolve into a vertical line segment than a horizontal line segment, because for this particular region I can definitively say that no matter where this point is located, if it evolves into a vertical line segment, it will definitely hit this curve as it moves up, and it will definitely hit this curve as it moves down. Whereas you can't say anything quite so definitive if you were to allow a point to evolve into a horizontal line segment. This point, for example, if it evolves into a horizontal line segment, bumps into the vertical boundaries. But this point up here, if it evolves into a horizontal line segment, bumps into that curve. So it's because of that ambiguity that I would rather consider vertical line segments than horizontal line segments. If I'm going to integrate with respect to y first then x, I would simply need to have equations of that upper boundary and the lower boundary. So if the upper boundary is described by the equation y equals g2 of x, and the lower boundary is described by y equals g1 of x, then that point is allowed to travel downward until it hits y equals g1 of x, and upward until it hits y equals g2 of x. And then I would simply need to collect up all such line segments from x equals a to x equals b. And in doing so, I would sweep out this region in its entirety, which is exactly what I want to do. I would integrate with respect to x first and then y if my region looked something like this. Okay, now that you already should know because we've spent enough time discussing double integrals. The reason I'm reviewing that is because we have to go through a very similar thought process when determining an order of integration and limits of integration for a triple integral. Only, of course, now it's going to be a little bit more challenging because we have a three-dimensional solid that we need to sweep out rather than a two-dimensional region. But initially, we apply the same thought process that we do for a double integral over a region. So what you want to do is consider a random point inside of that solid. And now ask yourself the question, if I were to allow that point, that zero-dimensional point, to evolve into a one-dimensional line segment, would I want to do so by allowing that point to travel in the x direction, in the y direction, or in the z direction? What would be most appropriate? And there might be no one single correct answer to that question. There might be multiple reasonable options here. So in this case, well, let's look a little more closely at what we're dealing with here. We have the paraboloid y equals 9 minus x squared minus z squared. That's obviously the red surface that you're looking at. But we're also considering the xz plane as a boundary. So only the portion of this paraboloid that lies to the right of the xz plane. And we're also considering the xy plane as a boundary. So the condition z greater than or equal to 0 means that we have to be on or above the xy plane. So that I believe explains the solid that we're looking at. The paraboloid y equals 9 minus x squared minus z squared is a paraboloid that has its vertex on the y-axis at y equals 9, and that opens in the negative y direction. So the solid that is bounded by that paraboloid, as well as being bounded by the xy plane below and the xz plane to the left. So that's our three-dimensional solid. Now, one very reasonable option in this case is to let that point, that zero-dimensional point, evolve into a one-dimensional line segment by letting it travel in the y direction. Because I can look at that solid and very clearly see that as that point moves leftward, it definitely bumps into the xz plane, and as it moves rightward, it clearly is going to bump eventually into the paraboloid. So I can clearly see what boundaries it hits when it moves leftward and rightward. And it doesn't matter which point I chose inside of the solid to perform that experiment. So integrating with respect to y first would make a lot of sense in this case. So as that point moves leftward, it bumps into the xz plane. The xz plane is described by the equation y equals 0. So my lower limit in y is 0. And as the point moves rightward, it bumps into the paraboloid. And as you can see, the paraboloid is given by the equation y equals 9 minus x squared minus z squared. So that would be my upper limit in y. Now what? Well, we need to eventually fill up this entire solid. And right now, all we've constructed inside of this solid is a single one-dimensional line segment. How do we sweep out the entire solid? The answer is we allow that line segment to roam upward and downward, in the z direction that is, as well as forward and backward in the x direction, until its left endpoint occupies all points inside of this semicircle. So what we have to do, and let me draw a separate picture here. In the xz plane, so I'm now looking down at the xz plane, kind of standing on the positive y-axis. What I see is a semicircle. It's a semicircle of radius 3, centered at the origin. And I think you can convince yourself that it is a semicircle of radius 3, because if you look at the equation of the paraboloid, y equals 9 minus x squared minus z squared, well, when that paraboloid hits the xz plane, y is equal to 0. And if I replace y with 0 in this equation, it becomes the equation x squared plus z squared equals 9, which obviously describes a circle in the xz plane of radius 3. So basically my outer the limits of integration for the middle integral and the outermost integral essentially they comprise a double integral over this region. And that allows this line segment here inside of the solid to roam freely in a way that it eventually sweeps out the entire solid. So if I now need to set up a double integral that sweeps out this region, I think I would want to integrate with respect to z next, knowing that z should vary from z equals 0, that's the x-axis of course, to z equals the square root of 9 minus x squared. I apologize for my messy writing here. I'm using a stylus and writing directly on a computer screen, and I'm not very good at doing that. But the limits of integration for my middle integral with respect to z would be 0 and the square root of 9 minus x squared. And that would correspond to constructing a vertical line segment inside of this region, and then I would want to collect up all such line segments from x equals negative 3 to x equals 3. So one important lesson I want you to learn from this example is that after you have determined which variable you want to integrate with respect to first, and once you have determined appropriate limits of integration for that innermost variable, from that point on, it becomes a two-dimensional problem. You've taken this variable out of the discussion, and now what you need to be looking at is the shadow that the solid makes in the plane of the remaining two variables. So this semicircle is really just the shadow that this solid makes in the xz plane. And all I need to do for my outer two sets of limits is set up a double integral over that two-dimensional region, something you allegedly already know how to do. Okay, so what you might want to try on your own, I don't want to spend any further time on this example, but maybe on your own, see if you can set up this integral as a triple integral in which we integrate with respect to z first, and then y, and then x. See if you can figure out what the limits of integration would be for that order of integration, and we can all compare notes on Monday. Until then, I'm going to move on to the next example. This next example might actually be a little bit easier. So this solid is called a tetrahedron, and it could also be legitimately referred to as a triangular pyramid. So it's the solid that has, it is a solid that has 4 faces. All 4 of those faces are triangles, and the vertices of those triangles are located there, 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 and at the origin. Now, this triangle that we're looking at most directly is formed by the plane, or it is a portion of the plane 2x plus 3y plus 4z equals 12. And I hope you all agree that that is indeed an equation of a plane, because it just has an x to the first term, a y to the first term, a z to the first term, and a constant term. So you should immediately recognize that as an equation of a plane. And it's also not difficult at all to ascertain that that plane intersects the x-axis. Whoops, the x-axis is over here. It intersects the x-axis at 6. It intersects the y-axis at 4. And it intersects the z-axis at 3. And you can deduce that very easily because this equation is satisfied by the point 6, 0, 0, which is right there, the point 0, 4, 0, right there, and the point 0, 0, 3, right there. So if we use that plane and the 3 coordinate planes as our boundaries, our bounding surfaces, we have this 3-dimensional solid known as a tetrahedron that could also be referred to as a triangular pyramid. Now in this case, it really is 6 of one, half a dozen of the other. The order of integration can be determined more or less arbitrarily. If you choose a random point inside of that solid, it really doesn't matter whether you allow that point to move in the x direction, in the y direction, or in the z direction. In each case, when it moves one way, it's going to bump into a coordinate plane, and when it moves the other way, it's going to bump into this triangle. So how about, for lack of a better idea, we integrate, f of x, y, z, we integrate in reverse alphabetical order. dz, dy, dx. Okay, so if I'm going to do that, I have committed myself to allowing a random point inside of that region to move vertically first. And as it moves downward, it bumps into this triangle, but that triangle lies in the xy plane, and the xy plane corresponds, of course, to z equals 0. As that line segment moves upward, it bumps into this triangle, which is a portion of this plane, and this plane has the equation 2x plus 3y plus 4z equals 12. Since we're integrating with respect to z, we need to have that plane's equation written in the form z equals f of x and y. So if we were to algebraically solve the equation of the plane for z, we would get 12 minus 2x minus 3y over 4. So those are my inner limits of integration. Now what about the middle limits and the outermost limits? Well, just like in the previous example, now that we've gotten one variable over and done with, what we need to do is look at the shadow that this solid makes in the coordinate plane of the remaining two variables. So in this case, we want to look at the shadow that this solid makes in the xy plane. Well, that happens to be precisely this triangle right here. So let's draw a two-dimensional picture down at the bottom of the xy plane. So this triangle intersects the x-axis at 6 and the y-axis at 4. And we need to set up a double integral over this triangle. And we've already committed ourselves to integrating with respect to y next. And so that means I'm going to build a vertical line segment inside of that triangle. So that vertical line segment travels from the x-axis, which of course is given by y equals 0. So my lower limit in y is going to be 0. My upper limit is going to be determined by the equation of that line. Now you should all be perfectly capable of finding an equation of a line that passes through the point 6, 0 and the point 0, 4 by first finding its slope and then plugging into, say, the point slope formula. But there's an easier way in this case. This line comes about when this plane intersects the xy plane. And when it intersects the xy plane, z is equal to 0. And so just take the equation of the plane and set z equal to 0. And we conclude that this line here must be the line 2x plus 3y equals 12. And you can easily verify that the point 6, 0 and the point 0, 4 both satisfy that equation. And that means that that line is given by y equals 12 minus 2x all divided by 3. Okay, so that builds this vertical line segment, and now I simply need to collect up all such line segments from x equals 0 to x equals 6. So that would be one way of setting up this triple integral. Now what we observe here, and that is very typical, the innermost limits depend on both x and y, and they are allowed to. When we're integrating with respect to z first, the innermost limits are allowed to depend on the outer two variables of integration. The middle limits of integration are allowed to depend on x, the outermost variable. And then the outer limits of integration have to be constants. All right, so there were 5 other options for this example. We chose to integrate with respect to z, then y, then x. We also could have gone z, then x, then y then z, then x, y, then x, then z, x, then y, then z, or x, then z, then y, but it's really is 6 of one, half a dozen of the other. You can try some of those other ways for practice if you like, and we can share notes, but it will quickly become rather tedious, so I'd rather move on and take the time to look at least one more example here. So on the next page, we have this solid right here, and it is the solid formed or bounded by the xy plane below, so bounded below by the xy plane, bounded kind of on the left by the parabolic cylinder y equals x squared. Okay, in 2 dimensions, y equals x squared describes a parabola. In 3 dimensions, the equation y equals x squared describes a parabola that is free to climb in the z direction. It opens in the y direction and has its vertex along the z-axis, as you can see. If you stand high up on the z-axis and look down at that parabolic cylinder from above, it looks like the parabola y equals x squared in the xy plane. So that's the surface that bounds this solid kind of on the left, and then the solid that bounds the surface the surface that bounds the solid above and to the right is the plane y plus z equals 1, which appears in blue in that figure. And the plane y plus z plus 1 doesn't have the variable x in it. An equation of a plane is not required to have all 3 variables in it. The fact that the variable x is missing actually winds up telling us that this particular plane is parallel to the x-axis. So it'll never intersect the x-axis. It intersects the y-axis at 1, it intersects the z-axis at 1, and the x-axis is parallel to the plane, so it doesn't intersect the plane at all. So this is what our solid winds up looking like. And if I were to place an arbitrary point somewhere inside of that solid, I think I would be perfectly happy allowing that solid to move upward and downward in the z direction, because if it does so, it's clearly going to hit the xy plane as it travels downward, and it's clearly going to hit the plane y plus z equals 1 as it moves upward. So that would be a good option. We may have also considered allowing the point to move leftward and rightward in the y direction. But let's go with this first route that I've identified. So I think integrating with respect to z first is a good option here. So as my zero-dimensional point evolves into a one-dimensional line segment by traveling upward and downward in the z direction, as it travels downward, it hits the xy plane. Whoops, I'm sorry, I wrote dx, I meant to write dz. Integrating with respect to z first. As the point travels downward, it hits the xy plane corresponding to z equals 0. As it travels upward, it hits the plane y plus z equals 1, which can also be described as z equals 1 minus y. Okay, so now we've gotten z out of the way. What do we do next? We need to now look at the shadow that this solid makes in the coordinate plane of the remaining 2 variables. And that, of course, would be the xy plane. If we look down at this solid from above, what we see is a shadow that basically looks like this. So that's a region that lies inside of a parabola, and that of course is the parabola y equals x squared, as well as lying below a certain horizontal line. Question is, how high is that horizontal line? That's going to be an important thing to know. Well, to determine that, you need to realize that this horizontal line is determined by where this plane intersects the xy plane. So we have the plane y plus z equals 1. If we want to know where that plane intersects the xy plane, we should set z equal to 0. Because on the xy plane, z is equal to 0. So if you set z equal to 0 in that equation, obviously the equation becomes y equals 1. And so this horizontal line that we're looking at off to the left must be the horizontal line y equals 1. So now for our outer two sets of limits, we need to set up a double integral that sweeps out this region. And I think it would make sense to integrate with respect to y next. So consider an arbitrary point inside of that region. Allow it to travel upward and downward in the y direction. As it travels downward, it hits the parabola y equals x squared. And as it travels upward, it hits the horizontal line y equals 1. And then, of course, the parabola y equals x squared and the horizontal line y equals 1 intersect each other at the points 1, 1 and negative 1, 1. And so clearly we want to collect up all such vertical line segments from x equals negative 1 to x equals positive 1. So that would be a very reasonable way of setting up this double integral, and as I say, there may be other options as well. Okay, let's try one more. Since I see I still have a little bit of time left, it looks like I'm still below 40 minutes. So we're going to take a look at this last example. This is a rather interesting one and kind of a challenging one to visualize. What we have here is a solid that is in the first octant. Okay, so that's stated, first octant. So in other words, above the xy plane, to the right of the xz plane, and in front of the yz plane. So the coordinate planes are all boundaries, and in addition, the cylinder x squared plus y squared equals 1 is a boundary, and the cylinder x squared plus z squared equals 1 is also a boundary. Now, in the figure on the left, it's the black cylinder that is given by the equation x squared plus y squared equals 1, and the blue cylinder x squared plus z squared equals 1. And I have maintained the same color coding in the figure on the right. So the figure on the right shows the actual solid itself that is formed by the intersections of these 5 surfaces, 2 cylinders and 3 coordinate planes. So it looks something like this weird looking wedge here that has one wall that appears in black and another wall that appears in blue, and the black wall comes from the black cylinder on the left, and the blue wall comes from the blue cylinder on the left. So that might be important to keep in mind. So how do we set up a triple integral over this solid? Well, once again, I think we could very easily go ahead and integrate with respect to z first, because I would have no qualms about inserting a point inside of that solid and allowing that point to move upward and downward. As it moves downward, it hits the xy plane, z equals 0. As it moves upward, I think you can convince yourself that no matter where that point was originally located inside of the solid, if it moves upward, it hits the blue surface. It's never going to hit the black surface if it's traveling upward, because that black wall came from the black cylinder in the figure on the left. And that black cylinder is parallel to the z-axis. So if you're just moving straight up or straight down, you'll never bump into that black cylinder, but you will bump your head on that blue cylinder if you travel up far enough. So the blue cylinder is given by the equation x squared plus z squared equals 1. And so as you move upward, you eventually bump into the surface z equals the square root of 1 minus x squared. Okay, so now we've taken z out of the problem, and that means we need to look at the shadow that this solid makes in the x, y plane. And I think you can convince yourself that because the cylinder x squared plus y squared equals 1 looks like a circle when we view it from high above, standing high up on the z-axis and looking down. The shadow that this solid makes in the xy plane looks like a quarter circle. Only a quarter circle because, remember, the solid lies entirely in the first octant. And in the first octant, x, y, and z are all greater than 0. And so we only want to consider the portion of the unit circle that lies in the first quadrant in the xy plane. So that's a portion of the circle x squared plus y squared equals 1. You can integrate with respect to y next and then x, or x next and then y. It's really not going to matter. So I'll just go with respect to y and then x. So to sweep out this quarter circle, I've got to let y vary from y equals 0 to y equals the square root of 1 minus x squared. And then collect up all such line segments from x equals 0 to x equals 1. So this is kind of an interesting one in which the upper limit in z and the upper limit in x happen to be exactly the same expression, and there's no rule that prohibits that from happening. The one rule that we do need to follow is that if we're integrating with respect to z first, then my limits in z are allowed to depend on x and y. They are not required to depend on both of those variables, or either of them for that matter, but they are allowed to depend on x and y. They are not allowed to depend on z. If we're integrating with respect to y next, then the limits in y are allowed, they're not required, but they're allowed to depend on x, but only x, not on y or z. So we haven't broken those rules, and so I think we're okay, and I think these are valid limits of integration for this solid. Okay, so I realize 4 examples aren't going to suddenly make you all experts at setting up limits of integration for a triple integral, but hopefully this was somewhat enlightening, and you should consider reviewing these 4 examples further and seeing if you can set up limits of integration for a different order of integration, because I think all 4 of these examples allow for more than one reasonable option for the order of integration. So practice that, practice some additional problems, take a look at your homework problems, and we will compare notes and continue this discussion on Monday. I see that I am about at the 45-minute mark, so this is a perfect stopping point, and we'll see you all on Monday.